So again, long story short, we're getting started in 1.5 today. Maybe get through that, hit 1.6, and then we'll jump into 1.4, all right, after. But, so if you're thinking, why am I covering one? If we're skipping 1.4, we're not skipping it, we're just delaying it until a little bit later. All right. So we're going to get into 1.5. 1.5 is on transformations of functions. Transformations of functions has a basic idea of, we're going to start with what the books call either base functions or toolkit functions. All right. Some books call these base functions. Sometimes books call these toolkit functions. It's the basic single operations, basically. And then we take those types of functions and we're going to move them, stretch them, flip them. And whenever we move them, or we stretch them, or we flip them, those things correspond to basic algebraic operations that you can do within the functions. So let's talk about what we mean by our base functions or our toolkit functions. There are things like f of x is equal to a constant number. The graph of f of x is equal to a constant number is a horizontal line. Another base function would be the identity function or the base linear function, which is f of x equals x. Now, this is not the only linear function, but this would be the base linear function. The base quadratic function would be f of x is equal to x squared. The base cubic function is f of x equals x raised to the third power, or x cubed. And so we know what the graphs of these functions look like. F of x is equal to x is a straight line going through the origin. The base quadratic function is this shape, which we call a parabola, whose lowest point is the origin. The cubic function, again, it kind of looks like a little bit of parabolic shape on each side. One on the right side pointing up, the left side pointing down, but it's going through the origin as well. So it looks like this shape. Other functions that we'll deal with are the following. The square root function starts at the origin and moves up to the right. And as you move further on to the right, it grows at a slower and slower pace. The cube root function is basically like the cube function turned on its side, like rotated and turned on its side. F of x is equal to 1 over x. Our book calls that the reciprocal function. 1 over x squared, our book calls that the reciprocal squared function. Another function of interest that we're going to look at right after this in the next section is the absolute value function. Hopefully we all know what the absolute value is. You plug in a number and it gives a distance from 0. F of x is equal to the absolute value of x. You get a v where the point to that v is the origin. When you graph that, it looks like 2 line segments emanating from the origin, one moving up to the right, one moving up to the left. Okay. Now, as far as this section goes, we will deal with the ones I've already mentioned. But later on, we'll deal with a lot of other base functions or toolkit functions, like exponential functions and logarithm functions, and sine and cosine and tangent, and other trig functions. Okay. And so later on in this course, we'll deal with other ones. And we'll define those other ones, those exponential functions, log functions, sine, cosine, tangent, other trig functions like secant, cosecant, cotangent. And we might even get some that I haven't listed. So once we can recognize these base toolkit functions, what we want to do is we want to start out by shifting them, moving them up, down, left, and right. Okay. When we move something up and down, what we do is we take the original function and we add a real number to that. We take our base function f of x, and then we say, let's do f of x plus k. That produces a vertical shift of the function f of x. On the other hand, if we want to produce a horizontal shift, then we have to, traditionally we write it this way, we adjust the inputs. Notice basically this plus k, we're adjusting the output. We're adding k to the output. Here, we're subtracting h from the input. The input is x, subtract h. And that's a horizontal shift. That should kind of make sense because our inputs are x values, our outputs are y values. So adjusting the output, shifting it up and down, shifting to y. Adjusting the inputs basically moves things horizontally. And you can adjust up and down depending on what the value of k is. You can adjust left and right depending on what the value of h is. Now, let's actually look at this on Desmos. Let's take a function. I'm going to take a base function, f of x equal to x squared. Okay. So this is our base quadratic. Gives me a parabola. And then I'll make another function, I'll call that one g of x, is equal to x squared plus some value. And I'll put, well, let's do actual numbers for a moment. If I add 1, notice what happens. Every point on the parabola gets shifted up 1 unit, right? If I added 2, meaning I created x squared plus 2, then every point gets shifted up 2 units. And the same thing would go if we did 4. Every point here on the parabola, like this 0.24, gets shifted up by 4 units. So by adding 4, we've shifted all of the outputs, all of the y values, we've added 4 to. What used to be a point on the parabola now is the point where we've added 4 to the y value. Okay. That's what happens when you add. When you subtract, it works the exact opposite direction. So if you add a positive number, you shift up. You add a negative number, shift down. Okay, every point on the parabola gets shifted. Now, to adjust the inputs, since our base function is x squared, we replace the x with an x plus or minus some number. I'm going to start with -1. So we replace the input with a -1. Notice that here, the input of -1 moves to the right. So x -1 moved it to the right. X -2 moves it to the right 2 units. -5 moves it to the right 5 units. And on the other hand, if we do +1, we'd move to the left. And this is why when people write the shift here, notice that the shift was written as x minus h. That way, if you think of it as x minus h, then positive h's move to the right, negative h's move to the left. Okay. And one of the nice things Desmos has is they have a feature where you can add a slider. And so you can see that as you move your h, the further you move it, as h gets bigger, the further you go to the right. As h gets smaller, you hit the origin, hit the actual, and then you start moving to the left. Okay. You can also add slider for moving up and down as well. Right? In this case, notice the plus k at the end. So then you're moving it up and down, left and right. And again, if you have a slider, you can do both. You can move it right 2.5 units and up 3.6 units if you want. Okay. Any questions about that? Straightforward. So that's why when it's written this way, it's written as f of x plus k, then positive k's move up, negative k's move down, and then f of the quantity x minus h, then positive h's move to the right, negative h's move to the left. All right, move the graph to the left. So if we're trying to determine how functions are shifted from an original function, I don't actually even need to know what the original function is. I can just look at something like this and say, well, if g of x is equal to f of x minus 7, I know that's a shift down 7 units. So that first one is a shift down 7 units in the y direction. This second one is a shift 3 units to the left. Right? That's the one to be careful on. X minus h, that'd be a minus a negative 3. So we're going to the left 3 units. So the first one is down 7. The second one is left 3 units. And then this third one is right 2 units and then up 10 units. So we go right 2, up 10. Again, x minus h, since this is a minus a positive number. That's right 2, and then plus 10, up 10. So I can determine shifts by not even knowing what the original function is. You can also take one of our base functions, or in other words, one of the toolkit functions, like f of x is equal to x squared, which is the one I obviously chose to do, and say, well, let's look at these particular functions, how they're shifted from the base function of x squared, f of x equals x squared. So the first one, that g of x, which is equal to x squared, x plus 2 quantity squared plus 5. That's a shift left 2 and up 5. You see that? So it's a horizontal shift left 2 and a vertical shift up 5. The second function there, h of x, is a shift right 1 unit and up 8 units. So right 1, up 8. Horizontal shift, right 1, vertical shift, up 8. So it's going to look like exactly what I've drawn here. In fact, we can confirm that there we go. Through graph. And you can graph on the TI-83 as well. It's perfectly fine. But there it is. Obviously, you can graph it without the sliders, and you see what's happening. Again, shift it right 1, up 8. Pretty straightforward. Good. By the way, why does a -1 shift to right 1? Anybody in their head? Think through that.
Because if you distribute it, it doesn't end up as a positive anyways because it's teaming.
Not in this case. Like that would be the same for not just squared. Yeah, the way I think of it is this. Normally, let's talk about that lowest point on the parabola, which is called the vertex. That happens at the origin with our base function of f of x equals x squared. In other words, when you plug in at 0, you get out of 0. Okay. When you do a -1, basically, we're asking, what do I need to plug in for x to get out of 0 in the x -1 squared part? Right, we'll ignore the +8 for right now. And you're basically saying, what do I need to counteract the -1? I need to plug in a 1 to counteract the -1 and get out a 0 again in that part. Okay. I don't know if that makes sense, but that's what it is. So it's adjusting the x value that you need to plug in to get the same output over here. Oh, forgot. Quick though. So now that we've shifted horizontally and vertically, now we're going to start stretching things. I'll explain what I mean by stretching vertically and stretching horizontally in just a moment. But if we have a positive real number, we'll call it A, then multiplying the function's output by A, we'll do a vertical stretch of the function. Multiplying the input by A, we'll do a horizontal stretch of the function. Now, we'll get into some of the details in just a moment. But when I say stretch, I'm talking about in the general term. Stretch could mean get larger, could also mean shrink, if that makes sense. So if A is a really big number versus a really small number, that might cause a stretch or a shrinking from our original function. If I multiply by 2 versus 1/2, one of those is going to stretch, one of those is going to shrink. That makes sense? All right. I'm using stretch in a general way. So multiplying the output produces a vertical stretching or shrinking. Multiplying the input by an A produces a horizontal stretching or shrinking. Which should make sense. When you multiply the output, you're multiplying the Y value. So you're getting a stretch or a shrink. When you're multiplying the input, you're multiplying the X value. And that's a horizontal stretch or shrink. Okay. Let's take a look at an example. We'll start with our base quadratic, and then let's just multiply it by a number. Let's multiply it by the number 2 on the output end. So after I've squared the ends. So here's what we mean by vertically stretching. 0, 0 had the y value of 0. If I stretch 0 by 2, 2 times 0 is just 0 still. Okay. Let me highlight a couple of other points. Notice that my original function, my base function, had a point of 1, 1. When we talk about vertically stretched, that point 1, 1, vertically stretched by 2, becomes the point 1, 2. Oh, forgot to break the comma. There you go. So vertical stretch means we're taking every point that we used to have and we're multiplying the y value by, in this case, 2. The same would be true for any other point. Notice that we had the point 3, 9 on our original function. If I vertically stretch that by 2, I should get the point 3, 18. Let me highlight the point 3, 9. Multiply by 2. Hopefully, we scroll up, my new stretched out graph goes through the point 318. So that's what we mean by vertical stretch. All of those y values, in this case, got doubled. Now, if they got tripled, I put a 3 in front of that, and every y value gets stretched out by a factor of 3. So that 3, 9 would now become 3, 27. And if I scrolled up far enough, oh, just had it. You'd see that it stretched out goes by 327. And what was 1, 1 now goes through 1, 3. Now, that's going to produce a vertical stretch. All of the y values are going to get stretched out as long as that a value is above 1. If the a value, if the numerical value in front of that is something like 1/2, then that stretch actually becomes a shrink, kind of gets cut back closer to the x-axis. So it was 1, 1, now it gets cut back to 1, 1, 1, comma, 1/2. What was 3, 9 now gets cut back to 3, comma, 4.5. All right. So it gets shrunk if that a value is small. Now, if we put the numerical value inside before the operation of squaring, let's put a 2 in here, then it gets changed horizontally by a factor of 2. So here we had the point 1, 1 originally. It got shrunk in by a factor of 2. So the x value changed to 1/2 and the y value stayed the same. Forget that. Notice, by the way, large numbers here are causing a shrink in the same way that subtracting caused a horizontal shift. Because I need to make my x value double to get the same output. Okay. Or I need to make my x value smaller to get the same output. In this case, or double. You guys get the point. And the same thing is true if I put a 1/2 inside there. I go from 1/1 now to 2/1. And my point that was 3/9 now got stretched out horizontally to 6/9. I need to put in double the x value to get the same y value out. Make sense? So it kind of works in reverse on the stretch shrink side. By the way, you may say we can use some algebra. In this case, we could have used some algebra with the x squared and written that in a few different ways. But the point is, if you multiply a number on the outside, you get a vertical stretch. You multiply a number on the inside to the input, you get a horizontal stretch, shrink. So let's take a look at this without any base or toolkit function. Just an arbitrary function f of x. And if I have g of x is equal to f of 3x, then I know that is going to be a horizontal shrink by a factor of 3. It's going to multiply all of the x values by a third, basically. For all of my old x values are going to get changed by multiplying by a third. So that's a horizontal shrink of 3. On the second one, that's going to be a vertical stretch of 5. You get larger in the vertical direction by a factor of 5. All of the y values multiply by 5. And then on the last one, that's going to be a horizontal stretch of a factor of 4, basically. Going to get wider. All of the x values you're going to need to plug in are going to be 4 times the old x value. I want you to answer this one on your own. Just here we have a different base function that we've been dealing with. We're going to move to the base function of the square root of x. And then just take a moment to decide. You can write it down. How g of x and h of x are stretched or shrunk from our base function. Say horizontal or vertical, stretch or shrink. All right, so g of x, is that a horizontal or a vertical? Yeah, horizontal, right? Horizontal because the 9 is underneath the square root. So it's horizontal, and it's actually a shrink of 9, factor of 9, because it's the inside. H of x is a vertical, and it's a stretch of a factor of 5. That makes sense? All of the y values are going to get multiplied by 5. And you can always check that out by just graphing each. By the way, if you're graphing the square root, you can write SQRT in decimals. On your calculator, obviously, there's a square root button. I haven't done the calculator yet, so let me do that. See if this. I don't want to do that. There we go. That's a round show. Good. Let me do it on the calculator this time. We did it on decimals twice already. So on decimals, you have the square root. There's a square root button on the calculator. Obviously, that's right here. So if I want to graph square roots, I can set y equal, clear out anything in there. And then I hit square root of, let's say, 9x. I can graph that and see how it's shifted from my base function. In fact, if you want to do your base function and that one, you can just graph it that way. Zoom, standard, that's what I'll do. So that's what we have. Okay. Might be hard to see on this, but because of the nature of how this is, but every point on here is traced back to something that has 1/9 the value as your x value. 1/9. So if I did, this one's kind of easy to trace. Let's do x equals 4. So obviously 4, 2. There you go. On the other one, if I typed in 4/9, I should also get it 2. Make sense? And that don't work for any version. If I had x equals 6 on this bottom one, notice the output is 2.4494897. On the other one, if I traced on the other one, I can change that by just hitting the up arrow. And typed in 6/9, I get that exact same output value. So whatever we type in on my original, type in that over 9, and you get the same output on the one that's been shifted. And the same works for 5x in a very different way. So that's my original, there's 5x, and what I would do is I trace, let's say we type in 1 here, I get 1, 1. If I go to the other, I should get 1, 5. Yeah,
On my calculator, because I have TI-83, I try to press graph that just says with arrow window range.
That would mean you would want to zoom standard, try the zoom standard there. Yep.
Yeah.
I can check it. It's something's with. You might also be on your stat plot. You might have stat plots turned on. Make sure you don't have any stat plots on too. That could be. If it says invalid dimension, that's probably more of a stats plots error. So make sure those are all off. And then you have to check it out. Okay. But should still graph the same way.
There it goes. Because I didn't have a stat plot.
Okay.
Thank you.
No problem. What was I doing? Oh yeah. So like for 2, on the original with the vertical stretch of 5, we should end up with 410, right? So I just hit the up arrow. Now I'm on the other graph. And although it's basically right at the top, it says, yeah, it's 410. So 4.2 on my original makes a 410 on this new graph. By the way, one thing you may have noticed or you may have not is we had our first graph that was square root of 9x. And we said that is a shrink by factor 9, right? But it's horizontal. We should all know that the square root of 9 is just 3. So that can also be written as 3 times square root of x. That's it. Algebraically.
But doesn't that make it vertical?
By how much?
3.
3. Yeah, this is a vertical stretch. By a factor of 3. So what we're saying is that those 2 different things are identical graphs. A horizontal shrink by a factor of 9 is producing the same graph as a vertical stretch by a factor of 3. And obviously we can confirm that. That's and that. Let's go back to the y equals. I'll put 9x in there again. But if you graph that, we've already confirmed that it is a horizontal shrink by a factor of 9, right? So let's just confirm that it's also, we could have thought of this as a vertical stretch by a factor of 3. So 1, 1 should also now translate to 1, 3. So I could have thought of this as shrinking every x value by a factor of 9, or I could have thought of this as enlarging every y value by a factor of 3. That makes sense. So, whoops. we had 4.2 in our original, now we have the 0.46. And sometimes that happens. Sometimes you can view the same graph in two different ways. Right? Now, if I give you a problem like this, I don't expect you to see that that's a vertical stretch by a factor of 3. You just say that's horizontal, shrink by a factor of 9, and move on, and you don't have to worry about it. But my point is that certain manipulations can get us the same thing. Stretching vertically and shrinking horizontally sometimes can be rewritten. Now, the next type of transformation that we'll do is flipping across the x-axis or flipping across the y-axis. And that's what happens when I introduce a negative. When I negate the output, we flip across the y-axis because we go from positive y's to negative y's, or vice versa. When I put a negative with the input, then we flip across the y-axis, because a flip across the y-axis is flipping the x values. Does that make sense? The y-axis is the line x equals 0. The vertical line, x equals 0. And so we're changing the x values from negative to positive, or vice versa. So that's a flip across the y-axis, when we change the x values from negative to positive. When we change the outputs, that's a flip across the x-axis. Now, I'm using the phrase flipping across the x-axis or flipping across the y-axis. Some people would say reflect across the x-axis or reflect across the y-axis. That's the same concept. All right. So let's take our function, our base function of absolute value of x. If I look at g of x, which is equal to negative the absolute value of x. Is that flipping across the x or the y-axis? X-axis, yeah. We go from positive y values to negative y values. So that is a flip across the x-axis, or a reflection about the x-axis, that g of x is. H of x is a reflection across the y-axis. I'll use Desmos on this one, so we can. There we go. So that's my standard absolute value of x function graph. If I put negative absolute value of x, and we're just typing in the vertical bars there, you can see that what you get is the red flipped across the x-axis, just like we said it was going to be.
Yeah. How do you put in absolute value on the calculator?
So on the TI-84, actually, let me just go ahead and do that real quick. See that? Good. if you want an absolute value, you have to go into the math menu on the left-hand side. And then scroll one to the right, and then it's ABS right there. So I'm in the math menu, so that button, and then scroll one to the right, ABS. And then if you have math print, it'll look like two vertical bars. If you don't have the math print, then it'll look like ABS and then in parentheses. So that's absolute value of X. And then I might as well do negative while I'm here. Absolute value of X. So should get the same thing. But yeah, math, and then the NUM, then U gives you numerical stuff. But there you go. By the way, interestingly enough, that's a flip across the x-axis. Notice what happens when we flip the absolute value across the y-axis.
Doesn't really flip.
Yeah, I mean, it's technically flipped. All the points are flipped. But because the graph was symmetrical about the y-axis, it didn't really change anything, right? Didn't change the shape or the look of our graph because of the symmetry with the y-axis. And on occasion that happens. So technically it flipped, but because of that symmetry,
It didn't really.
yeah, it didn't change any of the way the graph looked. There. Let's talk about transformations from base functions. And then if we had to, excuse me, if we had to graph by hand, how that could help us. So for instance, if we had this f of x equals 1/2 x to the third plus 4, hopefully we all recognize that the base function there is the cubic function. So that cubic function. Now here's the weird order of operations thing. Just like with order of operations, we're going to work inside out pretty much. So if I told you how to deal with this function, I would tell you the first operation outside of the base function is the multiplication by 1/2. So that's a vertical stretch shrink by 1/2, however you want to describe that. And then a vertical shift up by 4. Okay. Vertical stretch slash shrink by 1/2, and then a vertical shift up 4. And if I were to graph that by hand, I know what my base function looks like. And I can just use that to take my base function and graph this new one. I'll mute that, but I wanted to. So we know base function does that. And then I would shrink it by half vertically so everything can get closer to the x-axis. I don't know if I can do this real well, but still gonna look like this, but it's gonna be a little closer. It's gonna grow not quite as fast. Everything's gonna be shrunk down a little bit. And then I shift it up 4 units. Or whatever it is. So I go from there to there. And it's an easy graph. Does that make sense? If I had to do that by hand. Now, most of the time, we're going to have access to calculate. Well, we're always going to have access to calculators or Desmos or something like that. But if I had to do it by hand, I could do it that way. And it'd be a real fast process. Same thing over here. What I would do is I'd say, again, I work inside out, just like order of operations. You simplify what's on the inside, parentheses first, and then you move out and kind of get what I'm saying there. So what you would do is you would say the base function is the quadratic, the parabola. This is a shift right of 2, horizontal. Shift by right 2 units. And then I would flip. That negative is on the outside, so I'd flip across the x-axis. Axis. And then do a vertical shift up. You don't want to do your vertical shift before the flip. And you don't want to, it just makes things look weird. You can, it's not that big of a deal on this one. But the stretch, the shrink kind of throws things off. On this one, it's not very good. On this one, it makes sense. Think about if I would have shifted up 4 before I shrunk. And then, if I would have shifted up 4, this original point would have gone up there. And then I would have to shrink that by a factor, and I would not be at the same place. So the order of operations also take effect, or excuse me, take precedent when we are doing these shifts. All right, but where are we at here? So right 2, I'm just going to track the origin, the vertex, the lowest point on the parabola. Shift to right 2. Then we're going to take the parabola, what was pointing up, flip it, it's going to be pointing down, and then shift it up 1. So it's going to look like that. And again, understanding these shifts, these transformations, can allow us to easily see how graphs are going to look. Now, on the other side of this, if I know what the graph of a function is, I can say, well, that just looks like a shift of my base function, of one of my base functions. So you can look at this graph and say, this looks like a shift of the base function of f of x equals x raised to the third power. So it looks like base function of f of x equals x to the third. And it's going in the right direction, so it hasn't been like flipped across the x-axis or y-axis. Does it look like there's clearly a shift, horizontal and vertical shift here, but does it look like there's any stretch at all? How can you tell that?
It still just moves like 1 unit from the origin as it starts to slope. If that's a good way to say it.
No, you're absolutely on the right track. Are we hear that? So think of what happens when you shift away 1 unit from the origin. So our old origin, when we shifted 1 unit, we got to the point 1, 1. Okay. Just plug in 1, get out of 1, and the base function of x cubed. Over here, where our old origin was, is this point of, it's called a point of inflection. We go from here, if I move 1 unit to the right and 1 unit up, still on my graph, right? So that 1, 1 point is still 1, 1, just shifted over and up. That makes sense. So, yeah, it doesn't appear to be horizontally stretched or horizontally shrunk or vertically stretched or vertically shrunk because that 1, 1 effect. Okay. And if you go back and look at the base functions, let's go back and look at all of these base functions. Notice that when we go through the origin here, on our linear function is over 1 up 1, we're still at a 0.11. X squared over 1 up 1, still at 0.11. X cubed over 1 up 1, still at 0.11. Squared x going through the origin at 1, 1. Cube root going through the origin at 1, 1. Reciprocal doesn't go through the origin, but it does go through the 0.11. And same thing with 1 over x squared. It does go through 0.11. Same thing, with absolute value. It has that same like slope, that original slope. That original average rate of change from the origin, x value of 0 to x value of 1. That original average rate of change was 1. Does that make sense? We went over average rate of change last time, if you recall. So yeah, that is exactly what you're looking for. It's that slope. So now I know everything's basically shifted. So if I were going to take this function and rewrite it, I would say that we only have shifts here. The shift is left 2 and up 3. Be careful when you go left 2. That's not x minus 2, that's an x plus 2 inside the parentheses. Remember, going left to x minus h, the h shift. and then plus 3 on the outside of the parentheses. So it's the quantity x plus 2 cubed, and then plus 3 on the outside. Try this one on your own from the absolute value. Obviously, base function is absolute value. That's if you had to write the function, what would it be? So it looks like, obviously it's pointing down, so there's gonna be some sort of flip across the x-axis. So flip across the x-axis at some point, and then we have a right shift of 3, and then a vertical shift up by 4. And so it's gonna be negative absolute value of the quantity x minus 3, and then after that, plus 4. You can always confirm that by graphing. You can hit y equals, let's clear that one out. Clear that one out too. Just use your calculator. I wrote f of x equals, but you could have y equals negative absolute value of x minus 3 plus 4, and then graph that and see that you get the exact same thing. On the graph. Okay. Is that all right? Good. So can always confirm by graphing when in doubt. That's what you should do. Okay. Take a second to think about how this one would go. I'll give you a hint. There is a stretch or a shrink here. So I'm gonna go in a little bit improper of an order. All right, so I talk about this. Notice that the origin what on our base function, the vertex is the origin. Now our vertex has moved left 1, down 3. Okay. We also have this stretch going on. We can see that if we're at the vertex, if we move over right 1 unit, normally we move up 1 unit. Here, as we moved right 1 unit, we went up 2 units. So that indicates that there's a vertical stretch by a factor of 2. So a vertical stretch by a factor of 2, because instead of going over 1, up 1, we went over 1, up 2. That average rate of change from our vertex to 1 unit to the right is now 2 rather than 1. So there we go. So we're going to put a 2 in front, and then we're going to have quantity x plus 1 squared. And then we have to move down 3, so that's going to be a minus 3. So 2 times the quantity x plus 1 squared minus 3 should be my graph. And again, let's check that out. See if we are appropriate. Oh, thought I had that. There you go. Sure enough, that's the graph we got. 2 times quantity x plus 1 squared minus 3 gives me that vertex at -1, -3, and this point of 0, -1. Right, 1 up 2. All right, any questions about this so far? Transformation is pretty straightforward. Good. Now, the last part of this section deals with even and odd functions. I kind of hinted at this earlier about the fact that when you flip across the y-axis, the absolute value function didn't change. Because the absolute value function is a mirror image of itself reflecting across the y-axis. The fancy word for that is that the absolute value function is an even function. Mathematically speaking, even functions are functions where you plug in a negative x and you plug in a positive x and you get the same values, same outputs. No matter what the x value is, you plug in f of negative x and f of positive x, you always get the same output regardless of, or for all x, we'll say. Graphically, it means that it's a mirror image of itself reflecting across the y-axis. Odd functions are different. To have an odd function mathematically does not mean strange in mathematics. Odd function mathematically means when you plug in a negative x, you get the opposite of what you get when you plug in a positive x. And if you reflect, this says through the origin, some other people would say across the origin. You reflect through the origin or across the origin, you get a mirror image. So if I plugged in a 2 and got a 16, you would have been able to plug in a -2, got a -16. That's an odd function. May get that? You can also think of this in terms of ordered pairs. In terms of ordered pairs, the first two lines of both these are the same. In terms of ordered pairs, an even function, if I have the ordered pair x comma y, has a corresponding -x comma y. An odd function, if I have an ordered pair of x comma y, it has a corresponding ordered pair of -x comma -y on the graph. That's really what we mean by reflect through the origin. You just negate the x, negate the y on every point. So let's try to determine, excuse me, whether functions are even, odd, or neither. We'll do this algebraically at first, then I'll also show you how to do it graphically. So we're trying to determine whether f of x equals x squared minus 5 is even, odd, or neither. Or g of x is equal to x to the third plus 5x squared. H of x is equal to the cube root of x. Even, odd, or neither. Okay. So here's what we would do. If you're doing this algebraically, which we'll do right now on all three of these, all we would do is plug in -x and see what happens. If you can algebraically manipulate to get back to this original function, then I know it's even. If I algebraically manipulate to get back the negative of the original function, I know it's odd. If I can't get back to either of those two things, I know it's neither. Right? So in each of these, all we're going to do is plug in a -x and see what happens through algebraic manipulation. Now we have to be good at algebraic manipulation for us to be able to do this. That's the whole algebraic trick. So as far as this one goes, I would take -x quantity squared minus 5. And we have to know algebraically that negative squared is the same thing as positive squared. So that is the same thing as the positive x squared minus 5, which is my original f of x. Since f of -x is equal to f of x, I know this function is even. Okay. When I plug in negative x into g, and I algebraically manipulate, negative x in parentheses raised to the third power is the same thing as, well, if I take a negative and cube it, it's still a negative. So it's negative x raised to the third power, right? Negative times negative times negative is still negative. When I take negative x and square it in the same way I did here, negative squared is a positive squared. So this is the same thing as 5x squared. Now, this is not the same thing as my original function. So this is not even. G of x is not even. Excuse me. It's also not the negative of my original function. This term is negated, but this term is not. So this is neither g of x nor negative g of x. So that means my original function is neither even nor odd. On your homework, it'll be a drop-down menu. You just have drop-down, click even, drop-down, click odd, drop-down, click neither. So those are your three options. So it's neither even nor odd. This one, when we plug in a negative, the negative cube rooted is like a negative outside of a cube root. Everybody understand that? With a cube root, the cube root of -1 is -1. So you can use that rule to say cube root of negative x. It's like the cube root of -1 times the cube root of x. Cube root of -1 is -1. Notice that this is the negative of that. So this is negative h of x. So h of x is odd. Not too crazy, not too crazy. Good. Now, you can do that, plugging in negatives for lots of functions if you want. But I want to show you another way to decide even, odd, or neither. And that's just by graphing. I'll do that with these three first, and then I'll move on to the next ones. Okay. So, there we go. If I go graph, what what do we have? F of x equals x squared minus 5. And I look at that graph and I say, notice that, oh, I don't want that for me. That if I draw a vertical line through the y-axis, this graph is some, if I reflect across that vertical line, reflect across the y-axis, it's identical. Every point over here, reflected across the y-axis, produces a point over here. Every point over here, reflected across the y-axis, produces a point over here. Matching. So if you can look at a graph and say, yes, that is what we call symmetric with respect to the y-axis, therefore it's even. It can reflect across. So we knew f of x, we already knew that. F of x equals x squared minus 5. We saw that was even. That confirms it graphically. For the next one, it was x to the third plus 5x squared. That is definitely not symmetric across the x-axis. There's points over across the y-axis. There's points over here that do not have a matching pair, ordered pair over there. Matching point on the other side. Does that make sense? So there's points over here without a matching ordered pair over there. Definitely not. The other thing is we can see it's not odd. That might be a little bit harder to see right now, but it's also fairly obvious. We'd have to take every point over here shoot it through the origin, same distance, and create a point over here that corresponds. So go diagonally through the origin. You should get another point. Obviously, we don't have that. And then our last was the cube root. I always forget how to write that. That doesn't work. If I forget how to write cube root, there is a way to do this, but the easier way is to use exponents. There you go. Cube root is the same as x to the 1/3 power. This is not symmetric about the y-axis because, right, no matching pairs. But it is symmetric through the origin. Every point here, like -3.01, -1.44, has a matching ordered pair, has a matching point if I go through the origin. Follow that. So it's symmetric about the origin, and you can see that. And so if we look at other functions, now we have two different ways to deal with finding out if they're even, odd, or neither. You can either plug in a -x and see what happens, or you can graph it and see if we have symmetry with regard to the y-axis or with regard to the origin. And sometimes people like the algebraic approach. Like on this first one, this f of x, an example 11, I'd probably just plug in negative x and say, oh yeah, absolute value of negative x, same thing as absolute value of x. So that's going to be even. It goes pretty quick that way. Other times, maybe that's not as obvious. Let's take g of x and graph that one. X minus 2 cubed. Is that even, odd, or neither? That one's actually neither. It would be odd if this point were the origin. But we have to reflect through the origin. If I could reflect through the point 2, 0, we'd be all right. But reflecting through the origin means that, for instance, this 1, negative 1, come on now, that point would have to have a matching point of negative 1, 1, which it doesn't. And it'd mean this point over here, which is 3, 1, would have to have a matching, what is it? Negative 3, negative 1. Okay. So yeah, that's neither. Doesn't reflect, is not symmetric through the y-axis or the origin. And then the last, negative 1 over x. Again, you could probably do either. Doesn't matter. Ooh. Is that even, odd, or neither? Based on the graph. Yeah, that one's odd. Reflect through the origin, everything matches up. Symmetric with respect to the origin. By the way, there is another way people sometimes think of that. But yeah, I won't deal with that. There's more complex things. I want you to notice, by the way, on our base functions, here's where we get the name. Let me go back to this so I don't go back to my base functions. If I do f of x equals x raised to the first power, that is odd, right? If I said to the second power, that's even. That's an even graph. X raised to the third power, odd again. See how it's reflected through the origin? X raised to the fourth power, symmetric about the y-axis again, right? The phrase even function and odd function come from the powers of x on the base functions. So even, odd, even functions that's where you get the name. Now, not every quadratic, it's going to be even. We saw that if you do x minus something, it's neither. Also, if you did x squared plus 3x, that's going to be neither, right? But the base function powers, if they are x to a power, which is an odd power, then it's an odd function. If it's an x raised to an even power, then it's an even function. And when we graphed x to the third plus 5x squared, one component was an even, one component was an odd, we got an even. Interestingly enough. And if you go on and you keep moving on, you'll see that these other function types, like the cube root of x, and we'll see later some of our trig functions will be even and odd. They'll have what's called polynomial expansions that happen to be even and odd as well. That's not the scope of this class, but the even odd comes from the powers of x on a base functions. That's where the name comes from. Even functions, odd functions. All right. The other thing we can do with even and odd functions is because of the corresponding ordered pairs, we can decide where other points on the graph are if I know some initial points. So if I know that f of 3 is equal to 4 and f of negative 2 is equal to 7, if f is odd, then where does f send negative 3? Where does f send positive 2? If f is even, where does f send negative 3? Where does f send positive 2? Let's start with the odd. If f is odd, where does f send negative 3? Negative 4, exactly. Negative 4. They follow that? The output has to be the negative of where it sends 3. So, f of negative 3 is going to be negative 4. Where would f send 2 if f is odd? Negative 7, exactly. Negative 7. F of 2 would be negative 7. F of negative 3 would be negative 4 if f is odd. If f is even, where does f send negative 3? Just 4, exactly. Yep. If f is even, sends it to the same place that it sends 3. So 3 gets sent to 4, negative 3 would get sent to 4. In the same vein, f of 2 would have also had to have been sent to positive 7. We're getting that. So the negative inputs on an even function have to give me the same output if I input the positive number. On an odd function, we have to negate the outputs. We can do that graphically as well. Let's say I have a piece of a function, and I can see the graph of that function here. And let's assume f of x is even. Find f of -1 and f of -2. So what we would do is we'd start out by figuring out that f of 1 is -3, right? Based on the graph, goes through the point 1, -3. And therefore, if f of x is even, then -1 also has to be sent to -3. Everybody see why that is? So we know the function goes through the point 1, -3. So we have point 1, -3. And even means that the corresponding ordered pair needs to be -1, -3. Right? Negate the x value, keeps the y value the same. So negating 1 keeps y value at -3. And if same thing is true for -2. Now notice that when you plug in a +2, you get 0. This graph goes through the point 2, 0. So if this graph is even, or excuse me, if the function were even, then negating the 2 would give us the same output of 0. Everybody catch that? All we have to do is see which ordered pairs they went through, which the graph went through. By the way, the next slide talks about what if that same function were even? That we said was even was odd. So what if f of x were odd? If you know that the graph goes through the point 1, -3, what point what other point would we have to go through if f of x were odd? -1 comma what?
+3.
+3. Exactly. So when we plug in a -1, we're going to get out +3. So odd functions are flipping the sign from here to here. Even functions are keeping it the same. Here's the interesting one. If we know our function goes through the point 2, 0, what y value do we get out when we plug in a -2?
Also be 0.
Also would be 0, exactly. It would also be 0, because the negative of 0 is still 0. We follow that. So technically it's negative 0, but negative 0 is 0, right? 0 is neither positive or negative, so applying a negative sign to 0 gives me 0. Weirdly enough, that's what happens. So even when you plug in negatives, you get the same y values. Odds, you get the negative of the y values. And the one weird spot is 0, because you plug in a positive 0 or negative 0, and that's the same number. Does that all make sense? That's that. Like I said, that was the last example there. It's the one I just had written on the board. I didn't want to go back to the overhead. All right, so 1.5 was all about transformations of functions, and now, because we're into the looking at the graphs and the symmetry and all that stuff, we get a little aside on even odd functions. I'll get started in section 1.6. It's not a really long section by any means, but we'll get started there. 1.6, section 1.6 is on the absolute value function. And we've already seen the base absolute value function. F of x is equal to the absolute value of x. We saw how to graph that on the TI-84. And we graphed that on Desmos as well. I did anyways. And we know it looks like this. Now, this is the first function that we're going to start investigating. And in later sections and later chapters, we're going to investigate with more detail other types of functions. So chapter 2 is all about linear functions, and chapter 3 is all about polynomial functions. Chapters 4 is all about exponential functions and logistic functions. Then we're going to get into trig functions, and I might have my chapters mixed up there, but you guys get the point. So absolute value functions are the first ones we're going to deal with in depth, and we're going to look at some features of absolute value functions. When I'm trying to find some features of absolute value functions, I need some tools. The big tool is how absolute value works. We've already stated this, but I want to be more explicit here because of the nature of how I'm going to use this tool. If x is a positive number, then taking the absolute value of x is just like having x by itself. Absolute value of positive 6 is 6. Absolute value of 942 is 942. If I have a positive number, the absolute value of that number is just the number itself. On the other hand, if I plug in a negative number, the absolute value gives me the opposite of that negative number. So if I plug in a -2, I get back a +2. If I plug in a -8, I get back a +8. For that reason, the absolute value function can be written as a piecewise defined function with two outputs, one for positive values, one for negative values. Negative inputs, I should say. Positive inputs, negative inputs. That's going to be important when we go to solve absolute value equations. This is a tool that I'm going to need when solving an absolute value equation. So let's imagine I have an absolute value equation and I want to solve it. I'm just going to tell you how this goes and then we'll get into actually solving it in just a moment. If I have an equation that says absolute value of something is equal to b, well, if that b value is negative, then no solution. There's no output that's going to be a negative, no matter what I plug in for a. But if that b is positive, then because of the way absolute value works, I create two different equations. One based on the top part, one based on the assumption that the inside is negative, or excuse me, the inside is positive, and the other based on the assumption that the inside is the negative. Okay, understand that? So I'm going to say, here are two equations. A could have been equal to that B. Or the inside could have been equal to the negative of B. And then I solve each. So when we're dealing with absolute values, that's what we do. When we deal with an absolute value equation, that's what we do. If we have absolute value something equals B, and B is positive, then we create the inside could have been the positive B or the inside could have been the negative of B. And we solve each. Notice that here it says isolate the absolute value. There might be some upfront work to get to a stage where we can see that this is the absolute value equal to a number. So we want to isolate the absolute value piece and then break it up into two equations. So let's do a couple of examples here. We have x minus 2 inside of absolute values. Minus 7 is equal to 10. And then 3 times inside of absolute values x plus 1 minus 14 is equal to 2. So if I'm going to solve these absolute value equations, and again, this is the tool that I'm going to need to deal with find certain features of properties of absolute value functions that we're going to look at in a second, okay? So I'm trying to get this tool of solving absolute value equations set before we go back to finding features of functions. All right, so I'm going to isolate the absolute value. That just means get rid of everything else on that side. I want to add 7 to both sides. In this case, that's going to give me absolute value of x minus 2 is equal to 17. Okay. I wrote that one down right, didn't I? minus. Okay. And then we have absolute value equal to a positive number. So the thing inside the absolute value could have ended up being a 17, or the thing inside the absolute value could have ended up being a negative 17. Each of those equations is fairly straightforward to solve. Just add 2 to both sides. In the first equation, we get x is equal to 19. In the second equation, we get x is equal to negative 15. And we could ask, well, which one of those is the solution? They're both solutions, right? And if you wanted to, you could check that out by plugging those into the original equation. I'm not going to do that right now. But you can plug in each of those into the original equation, and it would give you a true statement. So both of these are solutions. And that's it. You write them both down. On the homework, it'll have 2 slots. And it'll say, write the bigger number here, the smaller number here, something like that. We can do the same thing over here. We would add 14 to both sides and get 3 times the quantity x plus 1 inside of absolute values is equal to 16. Then I would divide both sides by 3, and that would give me the absolute value of x plus 1 is equal to 16 over 3. You could write that as 5 1/3 as well, or 5.33 repeating, that's fine. And then we'd say x plus 1 has to be either 16 over 3, or x plus 1 has to be negative 16 over 3. I was going to say, subtract 1 from both sides. I do that in each equation. And now it kind of depends on how we want to write our answer. If you want an improper fraction, that's 13 over 3. If you want a decimal rounded to a couple decimal places, that's, I believe, 4.33, approximately. If Moodle asks you for the improper fraction, just write 13 over 3. If it asks you for the decimal rounded to a couple of decimal places, just type that in your calculator, get 4.33. Right? Nothing too shocking there. For this one, it'd be x equals negative 19 over 3. And that's negative 6.33 rounded to 2 decimal places. That's all. Pretty straightforward. By the way, the language here, again, some people put and, some people put or. in between these two, I'm not concerned. It kind of depends on the way you phrase the sentence. If it asks for both solutions, x equals 19 and x equals -15 are solutions. If it asks for which number can you plug in, you can plug in either 19 or you can plug in -15 and make the equation true. So linguistically, you can use and or in that sentence. But questions? Straightforward. Good. Take a couple of minutes to try these two on your own. These will be the last two we do today. That's 0.2x plus 4.5 all inside of the absolute value is equal to 7.2. Two times x minus 1. The x minus 1 is inside the absolute value, plus 10 is equal to 4. Excuse me. Okay. All right, let's go through this last couple of things. So first off, this one, the one with the decimal numbers, that already has the absolute value isolated on the left-hand side. So all we have to realize is that this means the inside component, negative, 0.2x plus 4.5 equals, that inside component can be 7.2 or it can be negative 7.2. In both cases, I'm going to subtract 4.5 from each side. So I end up with 0.2x is equal to 2.7. The other one, I end up with 0.2x is equal to negative 11.7. And then I would divide both sides by 0.2. If you feel more comfortable solving one at a time, you can solve one at a time. That's not a big deal. But when I divide this one by 0.2, I get a 13.5 as my x value. When I do this one, I get a negative 58.5. There you go, that's the 2. Again, this is the bigger number, that's the bigger number, 13.5 is bigger than negative 58.5, right? Bigger is referring to on the number line. So. For this second problem, what we're going to do is we're going to subtract 10 from both sides first. That will give 2 times the quantity x minus 1 inside of absolute values is equal to negative 6. Then I would divide both sides by 2. And you get x minus 1 inside of absolute values on the left-hand side is equal to negative 3 on the right-hand side. So what should I do next?
No solution.
Yeah, say that there's no solution. We have absolute value equal to a negative number. So at this stage, there's no solution. Now, if you tried to do it this way, you'd come up with 2 different numbers. But neither of those numbers, when you plug them back in, would have worked. Okay. So I always say, at this point, if it's absolute value equal to a negative, just write no solution and be done with it. Don't, solve it this way and then try to plug in and see that they don't work. So all I would do from here is say there's no solution. On the homework, if you run into something like this, I can't recall if they asked in this section for just writing NS for no solution or D&E for does not exist. But you'll have to write one of those 2 options in the blanks. Okay. On the homework on this one, it'll say larger answer is this, smaller answer is this, and you just write the numbers. On something like this, it'll say larger answer is this, you write D&E or NS for no solution or does not exist. And then the smaller solution, you say D&E or NS does not exist. Okay, no solution does not exist. All right, well, we'll pick this stuff up next time, Thursday. And other than that, I'll see you then. If you want to get started on the homeworks, you can do at least a couple of the homeworks right now. Okay.
sources.